this JLH amplifier. It's like a Halloween movie. Halloween 1, 2, 3, 4, and so on. So I'm stuck in this repetitive cycle or progressing cycle of making videos about this amplifier. If you haven't watched this series before, this is hood amplifier, to me, number 5. So the seller's page looks like this. I got it from AliExpress. I think this is the 1190 version. It was a kit. So we have some specifications here. And this is within a millimeter. And this is subject to some change. Design highlight 1. A high precision, high current voltage regulator output beyond the LM317. Now the 317 is a, I don't know, 5 to 30 volt 1 amp regulator. And we've got 2 more design features. So I looked at this and I thought, well, they've got some sort of a power supply device. This is the power supply. I commented that this has no independent voltage reference and no potentiometer. But I did go ahead and draw it up. I was mostly interested in the amplifier, which is from here on. This thing has an AC input and just bang right through the bridge to an 18,000 microfarad capacitor. And I call that voltage developed across the capacitor VCC. I didn't pay attention to this circuit here. And I call this output Vreg because this tells me it's a high current voltage regulator. Well, on closer examination, that's not what this is. I guess the easiest thing to call it is a soft start circuit. It's not a soft start in that it prevents the input power from being surged when it's turned on. The input power supply certainly draws a lot of current for a cycle or two, charging this capacitor. The only thing that limits the inrush current is the internal impedance of this capacitor, which is probably a tenth of an ohm. 2 voltage drops across 2 of these diodes. There's always 2 diodes in use in a bridge. 2 at a time, they alternate back and forth. And whatever the impedance of the external supply is. Once this voltage is developed, which I suspect happens in 2 or 3 cycles of the incoming AC, this voltage is developed. It's there. This voltage is not there because this transistor is not conducting. Why is it not conducting? Well, there's no base current. Where does it get its base current? Well, through VT4. When VT4 gets base current, it supplies base current to VT7, and all of a sudden this supply over here is developed. Where does the base current from VT4 come from? Well, it comes through R10, this 22K resistor. But when it's initially powered up, the majority of current that passes through this resistor does not go through the base. It goes over to this bank of 3 electrolytics, which is almost 150 microfarads total. So the current immediately goes up this way but most of it is diverted away from the base into charging these. As these charge, the percentage of current passing through here that goes to the base increases, while this current decreases. If we look at the voltage on these, we would see it slowly increasing, slowly being a relative term. But I have a hunch that the increase in voltage here results to an increase in voltage here. So it's a soft start on this portion of the amplifier. It's not soft start like you would expect in a motor circuit, for example, where you want to limit the inrush current. Inrush current is not limited. We'll take a look at that on an analog voltmeter. I have the meter connected to what I refer to as VCC. Actually, I've got it fastened to the collector of this transistor right here, which is right here. And you see I've color-coded VCC, and I've color-coded where it appears on the board. It appears here, here, whatever. Now there's a little bit of residual voltage left in this capacitor. I'm going to connect it up using this test lead and watch how the meter responds. Bang. Now there's response time in this meter, but as soon as I clip the lead on, you'll see it goes up to 15 volts. As quickly as the meter can move. Now I'll connect it to this, which is the opposite side of the transistor, the emitter. I'm actually connected to the collector of this transistor, which is there, which is also here. That's why the lead's over here. Now watch what happens. See how slowly it comes up? And there's also a 3-volt difference. We were reading 15 volts before, we're now reading 12. Disadvantage of this circuit is there's 3 volts drop across this transistor. But it gives us a very slow rise time. It doesn't change the time going down. Now it hits a residual there, so don't worry about that. But watch how slowly it goes up. I'll now connect to this point right here, which is the base of this transistor, R10, which is, I'll see if I can get on. R10 appears here. I think that's R10. You see that rise? Goes down pretty quickly. This is remaining charge. It goes up rather slowly. I'll show you what that means to when we have an input and an output. This will be the last few seconds of, I believe, 7A of this series. It dies rather quickly. but it grows rather slowly. Big capacitors. I've got a 24 volt transformer here. Although it's only producing 22 volts here, I'm a little bit disappointed by that. That does give me, at this point here, 24 volts. It gives me a VCC of 26 volts. This is the input. Right now, its peak to peak is 1.6 volts. The output, RMS, is 10 volts. Now I can turn that input up. You see what's happening? There, the input and the output are increasing or decreasing together. Right about here, things begin to happen. And this is 10 kilohertz, by the way. 10 kilohertz. I think that's as much as we can get out of it. 10.1 volts. RMS. Peak to peak is 21 volts. 21.6 volts. Now I have it terminated in a 8 ohm load. I've got a heat gun here, reading in centigrade. These transistors are not as hot as I expected them to be. 41 degrees C. Almost 42 now. That's this one here. 43 degrees C. C. I wish this heatsink had fins vertically rather than horizontally. Might get a more convection cooling. This is the absolute last. I'm going to talk about amplifier number 5. As I said before, all of these drawings, component spec sheets, are available down below. Thank you.